Okay, so I think everybody's drifting in now, so we'll get things going. So we're into the last session of this week's talks, and I think Danny's going to pick up with a few comments at the end. So to start things off, we're going to hear from Rebecca Frew with details about the volume of Arctic pack ice and marginal ice zone.
Nice, I'm on, good. Yeah, hi everyone, I'm Rebecca. I'm a postdoc at Reading, working with Danny, David, and Adam. And yeah, so I'm going to be talking about historical and future changes of sea ice volume budget for Arctic pack ice and the marginal ice zone. And I guess my sort of 5-year difference, so 5 years ago I was here and I was quite early on in my PhD using sort of a simple 1D sea ice mixed layer model. So now my model, I guess, has got a bit more going on. So I think that's my major change, and hopefully know a bit more. So getting started. So, okay, got it. Nice. So I think a few people have already talked quite a bit about the marginal ice zone, but I'll kind of recap and define as I'll be what I'm referring to, I guess, throughout the talk. So yeah, the MIZ, the marginal ice zone. So it's the wave affected region of ice. And I mean, using this sort of wave affected region can be quite tricky. Chris talked a bit about some work that has looked at using that. But in this talk, we're using the 15 to 80% sea ice concentration definition. And essentially because it's easier to use, we can compare with some satellite observations. So yeah, for ease of use. And also for kind of ease of use, anything above 80% sea ice concentration, we're referring to as pack ice in this case. So that's kind of what I mean as I go through. So yeah, so the marginal ice zone, we've already heard it's quite complicated, and we've got waves affecting the ice. So the marginal ice zone is defined like this. It sort of increases in the summer. We get this peak. So as the ice is fragmenting and the region, the MIZ increases, get this peak in the summer, and then before the sea ice minimum, kind of in the September. And the MIZ is generally, it's much larger in the Southern Ocean, but in the Arctic, we're kind of interested because the MIZ is expanding, and there's lots of potential for feedbacks with lots of like wave, ice, ocean interactions because of that increased open water fraction and larger number of small flows. So looking at observed changes. So this is from a study by Rebecca Rolfe in 2020, looking at satellite observations of the MIZ. So I think when they started looking at this, they were hoping that it would show an increase in the MIZ extent, but actually it stays relatively constant. So it's these dashed lines. So there's so this top one's a simulation that they did, and we have Bootstrap, OSI 450, and then it's AMSR ones as well. So yeah, so it stays relatively constant. We've got the different months here, but in terms of extent, but the MIZ is still widening. It's just moving northward, and kind of as a consequence of that, the actual extent isn't increasing. But it is forming a larger fraction of the sea ice cover. So you can kind of see as the sea ice extent in the solid line decreases, it's kind of, you know, getting closer to the dashed lines. So even though the actual extent isn't increasing, it's still forming a larger fraction. You also note maybe that there is quite a large range in the summer MIZ estimate. So in March, you can see they kind of agree relatively well, but as soon as we hit summer where the MIZ is larger, there's a larger range that we have. So I guess more difficulty at the lower concentrations maybe in that. So as I said, these changes in the MIZ are projected to change. So this study from 2017 by Yevgeny looked at projection. So we have the 2030s MIZ. So I think this is the 80% and this is the 15% contour, so showing the MIZ. And we can see that the summer MIZ width is increasing. And then this is the relative area of MIZ. So again, we see it's increasing quite sharp here. And we can see maybe like by 2050, it's kind of it's reaching over 50% there. So the aims of this study that I'm about to show is to look at the processes of essentially gain and loss of ice between the pack and the MIZ, or looking at these processes and how do they differ, what changes do we see, and what might become more important. So these are the sort of things we're trying to answer and look at. So in order to do this, we used a sea ice model, SICE, which we've also heard a bit about. So we used it coupled to a mixed layer model, and we've got a forced atmosphere. And I've listed a few of the sort of, I guess, a few bits of the important sea ice physics that we've got. So we do have in the version we're using, we do have the prognostic FSD model and the brittle fracture that Adam described yesterday. And I guess this is kind of particularly important in the MIZ, where we want some representation of the impact of, I guess, wave fragmentation affecting the flows and, increasing potentially lateral melt, the smaller flows. Form drag, and of course melt ponds, as Daniela has just talked about. And we've got this using this mixed layer model. So below the mixed layer, there's this restoring. Nice. So there are some limitations, I guess, to this using this model. So we don't have feedbacks with the atmosphere, and we don't have any ocean trends. So we don't have Atlantification, so like warming of that subsurface layer. But we do have some fairly detailed sea ice physics, and using this model, we can get a relatively good sea ice state, which is quite important to be able to look at these processes and get a good quantification. Nice. So I've included a couple of the observations again for comparison that have the longer records. So we have two simulations. So we have an NSEP. Sorry, I should say again, we've got the dashed is the MIZ like before, and the solid is the sea ice extent. So in purple we've got the NSEP force. So we go from 1980 to 2020, and in red we have Hajm, so going from 1980 to 2050. So we've done a kind of short projection. So, I mean, one thing to note, I guess, is in the simulations, we do actually get an increase in MIZ extent. It kind of is within the kind of range, which is sort of large, suggested by observations. But I mean, we can still kind of study these processes and see what we get. The other thing to point out, I guess, just in terms of differences, they agree relatively well, but we get a little bit steeper sea ice extent decline in the NSEP simulation, but they're relatively close. So I'm going to go through the different terms that I'll quantify later on. So in terms of gain, we've got condylation growth, so basal growth at the base of the ice, and this is kind of dominant form of growth. We've got snow ice formation. So this isn't so significant for Arctic sea ice, but is a more significant process for Antarctic sea ice. Get more snowfall and thinner ice. Potentially might become more important in the Arctic, I guess, though. And frazzle, so supercooling, and then we get the frazzle crystals, which collect. Nice. And then, yeah, our ice loss, so kind of self-explanatory, but basal melt, melting at the base of the ice, lateral melt, melting at the edges. So this is something that we would expect to become more important in the MIZ, the larger kind of perimeter top melt, so melt ponds, sublimation, yeah, kind of quite a relatively small term. And then dynamics, which is kind of quite a broad term here. So transport, convergence, and ridging, and we don't separate those out. So I've kind of put it in both because, you know, potentially it can cause gain in some regions and loss in others. The net impact is generally loss, but it kind of felt wrong to put it on one. So there was a study in 2021 by Keen et al., which looked at the sea ice mass budget in CMIT-6 models, and I think they had about 14 models which they analyzed that had the outputs, so they could do this. So there's some general sort of things to pick out, and this is well, say for the whole of the Arctic. I think they picked like there's a set region that they defined as the Arctic. So this is not just marginal ice zone, it's everything. So we've got the total melt here in black. So here's the basal melt, and you can see this is slightly too large. So this is the kind of the largest of the melt terms. So this one being top and lateral here as well. So we can see that the melting kind of peaks in July. We've kind of got a sharper peak for the top melting, and the basal melting is kind of more spread out. Lateral melting, we kind of can't see so much around everything else. It's kind of a much smaller term, but it, you know, is there. You see dynamics all year round. Yeah, and then we have the basal growth and the frazzle. Yeah, so moving on. Oh, one other thing, I think, so generally, yeah, so as I kind of said before, the basal growth, much larger than the frazzle ice formation, but I think this is quite sensitive to how they parameterized it. So a few of them had, you know, much closer ratios than this is, which is the mean of the 14 they looked at. So back to our simulations, and so the NCEP and the HAJM forced, and we look at we kind of looked at 3 different periods in order to kind of compare. So kind of label them. So low MIZs, where we have a much lower MIZ fraction, and we picked 5 years at the end of the 80s. We're kind of averaging over these 5-year periods, and we've got higher MIZ fraction where in the end of 2010s, where we where it's forming most of the here in August sea ice, and then in the end of the 2040s, end of our little projection, it's almost all of the summer sea ice cover. Yeah. So yeah, so we use these 3 different regions in each case we look at. So so these 2 are kind of covering the same region, for a little bit of comparison, I guess, of the HAJM4 simulation to kind of yeah, compare and maybe think a bit about yeah, the projection. So so the blue region, so it's pack ice in both the 80s and the 10s. The green region is the one we're kind of most interested in, which is the bit that becomes MIZ, and then orange is MIZ in both regions. So maybe it's a larger area than areas than you might expect, partly because we're looking at June, July, August average ice concentration fields from the simulations. So yeah, we get really large change here. I think something like 85% of the cover is MIZ in the tenths, and it's relatively similar in the two simulations. And then yeah, so in this one, most of the cover has already become MIZ, but we do get this region of change, and the region that's pack ice by this definition in both is very, very small. So we don't sum over these areas because it's very, very small. Nice. So yeah, so here are some annual volume fluxes, so a bit like figures I showed before. I'm sorry, there's kind of a lot going on, so I'll try and go quite slowly, and hopefully it will be kind of clear. So this top column, so these are the two comparisons of the 80s and the 10s kind of period, so the low and the high MIZ fraction. So the top row, we've got always the pack ice, middle is the becomes MIZ, and then this one is always MIZ. So yeah, blue 1980s, 2010s. We're kind of looking at the different regions, but the changes from the 80s to the 10s for each of the terms. So basal growth, frazzle, top, basal, lateral, sublimation, I put that there, dynamics, and snow ice. So kind of sublimation and snow ice are very, very small terms, so I won't really talk about them too much. So I'm going to try and pick out some bits out of all these plots here. So yeah, as I said, the top row is always pack ice, and again, much you might expect much smaller fluxes, smaller kind of cycle. In this region we've defined more multi-year ice, and we get kind of slightly larger fluxes, but in the Hadron force, which is one on the right, but they're kind of largely consistent, and we do see some increases, I guess, going into the 2010s, a bit of an increase in seasonality. Nice. So looking at the region that becomes MIZ, this is kind of where I guess we're most interested in, and so we see quite large changes. So we see quite a large change in both in growth and in melt. So in basal growth and in frazzle, we do see a sort of increase in sort of frazzle to basal growth, I guess, as that region becomes MIZ. And yeah, so there's this kind of balance, as we sort of also see obviously this increase in melting, and as we might have expected, particularly in the lateral melting. So it's still smaller than the other two melt terms, but it becomes much more important. So it's kind of interesting as well that the dynamics term, I guess actually I should have put it here, because it's causing sea ice loss, but it's becoming smaller, and it's not that the winds are becoming weaker or something. It's because there's just less ice, so thinner ice. So that sort of advection term is decreasing. So we see kind of similar in the Hadron force simulation, similar kind of pattern. There are some differences. So the initial fluxes in the 80s in that simulation are bigger, and we see some smaller changes. So the change overall was slightly smaller in this simulation. We kind of still see similar patterns, increase in frazzle, and this large, particularly increase in lateral melt relative to the other terms. Again, like I say, still kind of small, but becoming relatively more important. Yeah, so in the region that's always MIZ, we see reduction in fluxes, but we actually see the frazzle kind of, well, sort of increase a little here and stay quite constant, but the basal growth is decreasing. How are we doing? Nice. So moving on to the 10s and the 40s, so I'll kind of get rid of the other stuff in a minute. So like I said before, we don't consider this region because it's so small. And yeah, it's kind of more the same sorts of patterns in terms of obviously increasing growth, slightly more in frazzle, really strong increase in lateral melting. Yeah, and most of the ice is now in this region, so obviously you see really large fluxes, large seasonal cycle. Yeah. Nice. So kind of summary of what I just said. So in the region that becomes MIZ, see this large increase, in basal melting. See the amount of lateral melting relative increases is kind of compensated by this increase in growth and reduction in ice transport. And a similar thing in the 20s to the 40s. And in both scenarios, the proportion of ice growth that was frazzle increased, and the fraction of melting that was lateral increased. Nice. So the next thing I'm going to show is looking at the timing of some of these fluxes. So I've not put everything on it this time. So I've got the basal growth, top melt, basal melt, and lateral melt. So it's the same kind of setup. So in the region, we always have pack ice with much smaller fluxes, as you might expect, and they're kind of slightly later as well. Moving on. So I did forget to say. So the solid line is the 80s, and the dashed line is the 2010. So we're kind of looking in the change from one to the other. So it's much more obvious maybe here. So we can see, top melting peaking before the basal melt in the yellow there. And we can see how much this basal melt peak increases, especially in the NSET forced simulation. And that peak melting is kind of moving quite a lot earlier, so 10 days earlier in the NSET forced and 6 in this HAGEN forced. And maybe I haven't shown it so well, but we can also see that the lateral melting becoming a bit more significant there. We can start to see it comparable. Nice. So this region that's always MIZ, we sort of, it appears a bit different in terms of the top melting, quite a bit smaller compared to the basal melting there. And we also see this shift, and particularly in the end of melting and then the start of the basal growth. We're starting to see this region opening up. And then the final bit, so looking at the 10s to the 40s, so high MIZ fraction to pretty much all MIZ. It's kind of similar things, top melting, peaking, then basal. And we see a shift in the peak of melting. So if these combined move in 12 days earlier. Nice. And then these massive fluxes, and it's kind of same again, and it's quite a big shift. So the ends shifting by like 20 days. This is like 15. So this region is starting to open up, where in this region there's no ice. So summary. So peak melting occurring earlier in that region that becomes MIZ, and melting is then finishing earlier as well in the region where it was all MIZ in both. Sorry, tripped a bit there. Nice. And I guess kind of concluding remarks, slightly more hand wavy now. Lateral melting did become more important, or had larger volume fluxes. But I guess what this doesn't capture is that it's forming open, water, so its impact on the albedo feedback. So I guess what I'm trying to get at is potentially more efficient at forming open water than basal or top melt. So this kind of this isn't something we've looked at. So yeah, it depends how you look at it there. Yeah, frazzle became increasingly important, and in that study I showed, so the amount of frazzle forming is quite sensitive to the collection depth that's set and how the frazzle formations parameterize. So this is kind of I guess an area of uncertainty, and as it's becoming increasingly important, maybe something to think about. And yeah, I guess because we don't have the ocean trends captured within this study, so particularly in the 2040s, for sort of the longer timescale, maybe it's going to amplify melting, I guess, and that study doesn't include this. And thank you for listening. That's all.
Okay, thank you very much, Rebecca. Do we have any questions?
Thanks for the talk. I was wondering if you have that increase in lateral melt if you don't include a flow size distribution, whether you have those simulations?
That isn't something we've looked at, but would be interesting to compare.
So we also have a couple of questions from Siobhan Farrell in the chat. Firstly, are you saying in your forced Hadgen run by 2010 that the ice is less than 80%, or had that happened in the Hadgen run already?
So like in this plot or in the maps? Oh, right, sorry, can you repeat the question? I'm not sure I quite.
So the question says, are you saying in your forced Hadgen run by 2010 the ice is less than 80%, or had that happened in the Hadgen run?
I'm not sure I'm quite understanding that question. So this is showing for the average summer sea ice concentration, it's showing, yeah, the region in the 80s and the 10s that overlap in terms of the MIZ. So I guess in the 80s, the contour could be a bit further down for the 15%, but this is the 15%, I guess, for the 2010s and the 80. I'm not quite sure that's answering. Yeah.
We're guessing that the answer is probably yes. So the follow-up was, are you using CMIP 5 forcing or CMIP 6?
5.
Do we have any other questions?
I was just wondering, in these runs, is the ice model levitating above the ice, or is it embedded into the ocean surface? And does that matter for changes that you might see in the basal melt as you go forward in time?
So the ocean is just like a mixed layer. So I don't know if that partially answers your question. So it's not a full ocean model. So we do have, like the fluxes between the base of the ice and the mixed layer and the surface layer. Oh, right, I didn't.
It is levitating, yes. Almost all models do. Yep, all right. Thank you for an interesting paper. I think that the problem of freezing and melting of ice is very interesting, and I'm from a practical side, so it's also very important for us. I speak about that on Monday a little bit more, but I was interested in your definition of different mechanisms of melting, freezing and melting.
Yeah.
But in melting, I think it is a little bit different very often because there is very much melting at the crystal boundaries. Because I mean, if you do some sort of crystal potential, you see that those crystal boundaries are peaks, extreme values, and ice starts to melt there actually. And for columnar grained ice, that is quite important actually, because it makes it mechanically really very weak.
So I'll just add a follow-up. Do you account for internal melting in your budget within the interior of the ice?
No, we haven't.
Were there any other last questions just before we? So let Pat have the last word on this one.
Thank you. I'm very interested to see the increase in frazzle. Do you think that makes a difference to the mechanical properties, dynamics / everything else in the model if you end up having 50% frazzle instead of much less?
Yes. I don't think I can really comment on some of the differences, but yes, I think that would have some impact, yeah.
Okay, so thanks very much to Rebecca, and we should probably switch over.
Stop. Thanks.
Here? This one? Forward.